Welcome to Chandra's Edu. This is another video in the Artificial Intelligence playlist. I'm Chandrasekhar and I will provide useful content on different courses. And if you have not yet subscribed to the channel, subscribe Chandra's Edu as well as click on the bell icon to get regular updates. And coming to this video, we'll be discussing about the informed search strategies. In the last videos, we have seen about the uninformed search strategies like breadth first search, depth first search, as well as the uniform cost search. In this video, we'll see about the uninformed or heuristic search strategies. And what is the problem with the uninformed search strategies? So there is no bias. That means we don't know where is the solution. If we have any hint of the solution, then we will try to search in that path to find the solution. So there is no bias. That means we have no knowledge about the where the solution is. So in that case, what we need to do is we need to search everywhere to find the solution, so that the complexity of uninformed search is intractable. That means it is very hard to find the solution in the uninformed search strategy. Suppose if we have some hints for finding the solution, then that can be called as the heuristic information. That can be called as a heuristic information, and we'll try to use that hint to find the solution. Suppose in this a bigger tree, suppose that the solution is in this tree branch itself. So we are trying to limit the search to this branch so that we can find the solution in an easy way. Rather than just checking for the every tree branch, we will specifically go into this tree branch to find the solution. So what happens due to this is the speed will be increasing and the efficiency of the search. That means we are putting lesser effort to make the search to find the solution. And also the complexity, as we have seen in the uninformed search strategies, if we take time complexity or the space complexity, if b is the number of branches and branching factor and d is the depth of the goal node, then the complexity will be O of b power d, that is exponential time complexity to find the solution. Even it is for the space complexity also. So when we go for the heuristic search or informed search, so the branching factor will be there b as it is, but we are going for another factor called as b star, which is a very low value compared with the b. So it may be even equivalent to 1 also, so that the branching, as it is a very smaller value powered with the depth, the search will become very much easier, or we can say the time complexity will reduce, as well the space complexity also will reduce. Next we'll see about heuristic functions. So heuristic, as we have seen in the last slide, it is nothing but a hint to find the solution. So here heuristic function means, so that gives an estimation, it gives an estimation of getting from node n to the goal state. Suppose we are at a node n, and this is the goal node, and this is the starting node. So we are at node n now, and we have come from starting node to node n, and from n we need to go to the goal node. So that is nothing but goal state. So we are at starting state to n state we have come up already, and from n state we need to go to the goal state. So that function which will try to estimate what is the distance between the n state, or we can say node n, to the goal node, so that we call it as the heuristic function. So if we try to estimate that, we'll try to see whichever the function, that means by calculating function from n node to the goal node, there can be different ways of reaching to the goal node. So whichever node is having the lower cost, it may be distance, it may be a straight line distance, there can be different factors by which we can represent the heuristic function. So we'll take that parameter, and based on that, whichever is less, we'll choose that and find the solution. So what happens here is the least cost among all possible choices can be selected for expansion first. So we can go this way to the goal node, and we can go even this way to the goal node. But we'll try to prefer this way. Why? Because suppose this is the here is another node and here is another node. Here it is 5 and here it is 7, and here it is some 6, and here it is 8, and suppose that this total path is nothing but around some 6. So here 6 plus 8 is 14, and 5 plus 7 is also 14. Okay, if we sum up these costs, it is 14, and even this cost, it is also 14. But when you take this path, it is only 6. So we'll always try to prefer the lower one, that is 6, for reaching the goal node from the nth node. So that is called as the cost estimation, and that we can call it as the heuristic function. So there are three approaches of defining a that is heuristic function. So we are just representing it by using f or f of n. So f of n measures the value of the current state. So it is we can call it as goodness also. So we'll see in detail about what is goodness. And the second approach is nothing but estimated cost of getting to the goal node from the current node. So here also we discuss the same example. We are at node n and we are trying to reach to the goal node. So that distance also can be called as the heuristic function. And other way we can take this heuristic function is, we'll consider the distance from this starting node to the node n, as well as from node n to the goal node. So that two costs we can consider, and even that also can be called as a heuristic function. So g of n is nothing but cost from the starting state to the nth state, or we can say starting node to the nth node, and the h of n, as we have seen in the last approach. So h of n is nothing but the cost from the nth node to the goal node. So if we combine those two, also we can call it as a heuristic function. So we'll see in detail about these three approaches in the coming slides. The first one is nothing but measuring the value of the current state. That is approach 1. So here it is mostly used in the optimization problems, in solving the optimization problems. So sometimes the distance may be factor. Sometimes safety may be the importance. Safety is of importance. So whatever the value we are giving at that point of time, so that can be called as a heuristic function in the approach 1. So finding a state such that the value of metric f is optimized. That means sometimes lower cost is nothing but the optimization required. So whatever the lower cost distance is there, we'll try to prefer that one. Next, suppose that if we think that there are some 3 routes and 2 routes are safe, there is 1 route is safe and other 2 routes are not safe. So we'll try to prefer a safer route. So there can be different parameters of optimization. So that optimization is nothing but considered in the approach 1, and that we call it as a heuristic function. So here so we can even consider all the parameters also as the weighted sum. That means, so if parameter 1, parameter 2 and parameter 3 are nothing but the factors which need to be considered for optimization. So suppose that parameter 1 is very important. So we can give, suppose that the total weight is 1, then we can give this total weight of this parameters is 1. Then you can consider this as the 0.6, and this is having somewhat there is 0.3, and this with the 0.3. So 0.3, that is 9, sorry, 0.1 should be taken. So total it will become 1. So the total factor is nothing but divided across these parameters. We can give an weighted value for this optimization function. If we have more parameters, we can give the weights for each of the parameter, and that also can be considered as a heuristic function. We are taking here two examples. That is, one is nothing but n queens problem, where we need to place the queen, where we can just take a checker type of board, and so these are the checker boxes. Suppose the queen is placed anywhere over here. Then in the next column, we need to place the queen such that it will not cross horizontally. That means you can have either this one or this one for the placement of the next queen. So that is what the optimization we need to consider when you are going for n queens problem. Suppose data mining we are taking as the example. Then we can consider here accuracy or predictiveness. Predictiveness means within how much time we can expect the output, or how much accurately we can access the data. So that can be considered as the optimization factor. So that is about the approach 1. Coming to the approach 2, measures the cost to the goal. So as I told, we are just at goal at we are at the node n, and we need to reach to the goal node. So from n to, suppose we are at a node n, which is not the starting node, and we need to reach a goal node. So whatever the distance from this the node n to the goal, that we call it as the heuristic function in the approach 2. So there can be different ways of reaching this goal node. We can just prefer the one which is the best. So that we call it as a heuristic function. So here we are taking an example of 8 puzzle. So where we have different that is nothing but 8 numbers, 8 tiles which are placed in different places, and this is what the starting state is, and we need to finally arrange in the goal state like this. So here there can be different parameters. That means suppose that it is at a place where we have, suppose that 1 is at this place, 2 is at this place, and so 3 and 5 is here, and 6 here, 7, and here it is some, okay, here we can consider 8, and here it is 3, and here it is 4. So this is one arrangement. So to reach to the solution, what we can do is we try to move 4 this side, okay, so that 4 will be here, and we'll try to move 3 this side, so 3 will be here, so that it comes to the goal state. So that distance, that means we are considering this as one state. What is the distance from this point to this one is nothing but only one is the distance. That means why? Because not one, why? Because we have taken here 2 steps, we can call 2 steps, okay, 2 steps. So like that there can be steps to reach to the final state. So here we are taking two up that is 2 cases. One is nothing but h1 is nothing but number of misplaced tiles. So this is one type of misplacement. Why? Because 4 is not in this place, and 3 is not in this place. So there are 2 misplacements. So how many steps you need means 2 steps you need to get to the goal state. And even we can consider the distances, sum of distances of tiles from the goal positions. That means we can just take what is the distance? Actually 1 should be here. So what is the distance? As it is in the same position, the distance is nothing but 0. So 2 is here itself. Suppose that if we take a case where we have, so 1 here, 2 here, and 3, 4, 5, 6, 7, 8. So this is the case. So as per the goal state, what is the distance to 1 to be here? That means it should move 1 position to reach to that. So distance is nothing but 1, and this one, it is nothing but it need to take one move to reach to the final state. So you can consider two steps. Why? Because we need to move 1 to this position and 2 to this position to reach to the goal. So here also you can consider two steps. So what we are taking here is one step of 1 and one step of 2. So total of 2 steps. So there are different approaches. We'll just consider here what is the distance from the node n to the goal node. That is a second approach. Coming to the third approach. So third approach measures the total cost of the solution path. So here we can call it as the admissible heuristic function. Why? Because it considers whatever starting node is there, from that point to some node n which is in between, and from that node n to the solution. Starting node and some node in between, and here is the goal node. So whatever the distance we have from source starting node to the goal node, sorry, n node, and from n node to the goal node, that total distance we are considering under the approach 3. So when we take this type of, that is g of n is nothing but this one, and h of n is nothing but this one. So is admissible if h of n never overestimates the cost to reach the goal. So if we know this distance, sometimes there may be chance that h of n overestimates, and in that case we can't get the optimistic solution. So here you can find admissible heuristics are optimistic. That means if we consider that is starting node to the node n and node n to the goal node, then we can find the optimal solution. The cost is not that much. That means sometimes it may be optimistic, sometimes it may not be. Why? Because so here we are measuring up to starting node to the node n, but sometimes this point, that is node n to the goal node, that may not be an optimistic value. Next, g of n is nothing but exact cost to reach to the node n. So here, as it is, h of n is nothing but an estimation. It can take different paths, but whatever g of n is nothing but it is the actual cost from the starting node to the node n. That is initial, from initial node to the node n, that is nothing but the exact cost. F of n never overestimate the true cost to reach to the goal state through the node n. Why? Because f of n is nothing but sum of g of n and h of n. So h of n is nothing but the exact cost from the starting initial state to the node n. But h of n, it can take any estimation. Why? Because there are different parameters that can be considered, and if at all, if it is admissible, then we can get a optimal solution. But if it is not admissible, then what happens is the estimation will become more, and whatever this the reaching solution, it may not be an optimal solution. So a search is optimal if h of n is admissible. Whatever this parameter, if this is admissible, then the solution will be optimal. The search using h of n returns to an optimal solution. So as I told here, h of n can be any parameter. It can be h1 of n or it can be h2 of n. But if h2 of n is greater than h1 of n, then we'll try to prefer whichever is the lesser one, that we will try to prefer. So you can see here h2 more efficient to use h2 of n. Here the greater indicates it takes the lesser time, or we can say lesser cost, so that h2 will be more preferable than h1. It is not about the distance. h2 takes the lesser cost and h1 takes the more cost. Here h2 is greater than n, h1 indicates that h1 can reach to the solution in a faster way than h1, so that h2 is more preferable or more realistic than h1, and it is more informed also. Why? Because we can reach to the solution in a lesser time. So even though both the solutions are acceptable, both solutions are acceptable, or both solutions seems to be optimistic, but H2 can be more realistic ones. Why? Because it can take the lesser time to reach to the solution. Next, we have greedy best first search. This is the informed search strategy, and we have also the A star search. These are the two main uh, informed search strategies. So in this greedy best first search, so we'll always try to take H of n, that is nothing but approach 2 which we considered. Always choose the successor node with best f value, where f value is equal to h of n. That means we are at some node n, and from that node, what is the best way to reach to the goal node. So that we are trying to see in the greedy best first search. So we choose the one that is the nearest to the final state among all possible choices. So we are just trying to be greedy to reach to the solution. So that is what it got its name, greedy best first search. Next, coming to the A star search. So best first search using an admissible heuristic function. As I told, if f of n is admissible, then whatever the solution we get in that informed search strategy, that will be more realistic one, and we can get the optimistic solution. So whenever h of n is optimistic, then g of n is also h of n is admissible, then g of f of n is also admissible, then we can get the best solution, or we can say we can reach to the solution in the with the lesser cost. So best first search, the same best first search we are using with an admissible heuristic function f of n that takes into account the current cost g of n. That means it takes f of n. For the best first search, we are taking only h of n, but we are also considering g of n. Then it becomes the A star search. So always returns to the optimal solution. Why? Because this one we are all this gives an exact distance from the initial state to the node state, node n. But from n we have different paths h of n. So we will be choosing here admissible h of n, so that we will get admissible f of n, so which gives the optimal solution. So first we will see about the best first search, that is nothing but greedy best first search, the first informed search strategy. So here we are giving the function that is best first search. For that we are just giving the problem as the input, as well as the some function for evaluating the cost. So what it returns is a solution sequence. Solution sequence, that means the states by it need to pass to reach to the solution, or failure. That means if at all it can't reach to the solution, that is nothing but a failure. So here we take one queuing function. Queuing function indicates the set of nodes it is passing in the sequence. Just whatever the node which it has passed through, it will be just storing in the queue. The function that sorts nodes by evaluation function. Why? Because whenever it is passing, there can be different paths to the solution, but it will be choosing the one which which it sorts according to the path cost or evaluation function. So what it finally returns is nothing but the generic search. The total function will be returning the generic search to find the solution. So as it's a greedy search, f of n is nothing but h of n. Evaluation function here is nothing but, so here we require an evaluation function. So that evaluation function is nothing but the h of n. So here in the search problem, in the generic search problem, the problem is nothing but the whatever the problem we give for the searching process, and here we get the queuing function. Queuing function is nothing but the sequence of the nodes which it will be passing to pass to get to the solution. So here is one example. Here we are considering h of n as the, or we can say the heuristic function as the straight line distance heuristic. Straight line distance heuristic. So that means straight line means whatever the path we have from the starting node to the goal node. Okay, that is nothing but the starting node or any other node in the tree. From that node to the straight line, if we draw to the goal node, what is that distance? Suppose that if you are taking node A, if we draw a straight line, it is nothing but I. So the distance is nothing but 366 is the distance. So we can see here, if we draw a straight line from this one to the goal node, that is nothing but 366. Suppose if we take node B, the straight line distance from this B to the I, it is nothing but 374. Like that for every node. Node C 329. So you can see the straight line path from C to the I. So it is not the cost which is mentioned on the, it is not according to the cost which is mentioned on this directed path, but it is a straight line distance from that node to the goal node. We can take it any node. Why? Because it is nothing but node, this can be considered as a node n. Here h of n is nothing but the straight line distance, that is equal to that is for the C, what is that? 329. H of n is nothing but 329. Like that we can take for every node. So if you are taking node D, so it is straight line distance is nothing but 244. And next coming to E, it is 253. This is 253. Next we have F node, that is 178. So 178. See here, even F from F to goal node also there is a path which is of 211. But when you take a straight line distance, it is less than that. That is nothing but 178. Next, if we take go node G, that is to the final state, that is goal state I, it is nothing but 193. Next from node H, so here also you can see if you take the distance path cost, that is nothing but H to I is 101, but if you take a straight line distance, it is 98. So this path cost is different from the straight line distance. Here straight line distance is nothing but considered as the heuristic function. So heuristic function can be different from the path cost. So next, if we take the node I itself, as there is no distance at all, it is nothing but 0. So now we need to go search the tree to find the solution using the heuristic function. So as we have taken the straight line distance heuristic function, this is the table, whatever we have seen from A, B, C, D, I. So till the goal node I. So what is the distance? Straight line distance. So that is nothing but here, it is nothing but straight line distance heuristic. Straight line distance heuristic. And if you are at node A, node starting A is nothing but goal node A. From that point, we need to just see whichever node we can reach with the lower cost. We can just see there is a path to C, there is a path to B, and there is a path to E. But we need to just see from which node of this C, B, E, the straight line distance is less to the goal node. From C, you can see 329 is the distance to reach to the goal node. From E, it is 253 is the distance to reach to the goal node, straight line distance to the goal node. And if we take B, the distance is nothing but 374 to reach to the goal node. So among these three, we have 253 as the lesser number, so that A, from A it will be taking the next path to the goal node E, which is nothing but 253. Next, it will try to see the cost from E. So from E, we have paths to G, next A and F. So I have considered the same, that is nothing but from A, just see C, E and B. The same path we have drawn, C, E and B. Next from we have chosen E. So from E the path is to G, the path is to F. Also we can even go back to A also here. So we can even go back to A, so that even that path is also considered. We can just take path to G, path to F, as well as path to, so path to G, as we have known, path to G, path to F, as well it can even go back to A also, so that the three paths are given. Actually in this tree we have only two paths. From E we have path to G and path to F, but coming here in the tree we have drawn path to G, path to F, along with that the path to A also. Why? Because it can even go back to A to find the heuristic function. So among these three, G, A and F. So A it is 366, and next G it is 193, and the other one is F, which is 178. So among A, G, F. So among these three, 178 is the lesser one, so that F node is considered. So this node is considered next. And from the F, just observe the tree. So from F we have only one path to, there is the only one path, that is nothing but to the goal node. But even I told that we can go back path to check for the h of n to find the solution. So that we can have two paths here. One is nothing but F to I, as well as F to whatever path it came from, that is E. So we are drawing the two paths, that is F to E and F to I. So from that we need to just check F to E. So F, that is E, 253 is the distance, and F to I. So F to I is nothing but the straight line, that is distance. E it is 253 and I it is 0. F is nothing but 250, sorry, E is 253 and I is 0. So that we'll prefer this path to reach to the goal state. So here there are two parameters. One is nothing but the path cost, other is nothing but the distance. So distance here means straight line distance. So if we consider the path cost, so path cost means we need to take into account the path from A to E, E to F, F to I. So these path costs are already mentioned here, A to E, E to F and F to I. So we have A to E 140, E to F 190 and F to I 211. If we take that path cost, 140. So the distance is nothing but whatever A to E, E to F and F to I. So that total cost is nothing but 450. The total is nothing but 450. And if we take here the straight line distance which we considered, so that is the actual distance which we, that is the actual distance from the starting node to the goal node. That is the total distance from starting node to the goal node, as it has passed through A, E, F, I. But when we take path cost here, so the path cost includes the heuristic function. So heuristic function means, so it need to take into account what are the costs, path cost which it has passed, so that we got the solution. So it has passed to E, and from E to F, E to F and F to I. So if we take that, A is not considered. Why? Because it is the starting point. So we need to consider the straight line distance from E, which is nothing but 253. And next it has passed to F. So from F the straight line distance is 178. And from lastly it has reached to the I. Straight line distance is 0. If we sum up all this, we got 431. So the distance, if we go by the approach of the normal distance approach, that is our path cost, we can say, it is nothing but taking 450. But when we go by the straight line distance, that is heuristic function, h of n straight line function, straight line distance, if we take straight line distance for the h of n, if we go by this approach, the cost we are getting is nothing but 431, which is lesser than 450. So that is what the solution we can find, and we can say that by using the straight line distance, we can reach to the solution faster than the normal path cost approach. But we need to see whether it is an optimal one or not. So when you take the the first one, that is we need to see about different parameters. So in that first one is whether it is an optimal one or not. So this is what the normal tree which is given. Earlier slide also you can find earlier slides. So where we have the actual tree given, actual graph given. So from that we are just checking the straight line distance here. So we have different paths to reach to I. But if we take a different path, so in the earlier slide we have seen that we have gone through the path A, E, F, I. So that is the path we have followed, and whatever the cost we got is 431. Suppose that if we have taken A, E, this path if we have taken to reach to the solution, then if we consider the distance here, the normal distance, normal path cost distance, 140, 80, 97 and 101. So if you take that cost, that will be 418 itself. That will be 418. And here, if we take this distance, if we take the normal distance, it is 450. And here it is 418. Here we are not taking the straight line distance. Even if we take the straight line distance also, 253 plus 253 plus G is nothing but 193 plus H is nothing but 98 and I is nothing but 0. Okay. So if you take that cost, so 3 plus 3, 6, 6 plus 4, 6 plus 8, 14, 1, 18, 14, 20, 14, 13. So 444 we are getting. 444 we are getting. But here we got 450. Even if we consider straight line distance also, here we are getting 444 and here we got 450. Even if you take path cost also, path cost it is taking 450 and the straight line distance it is taking 431. And here the path cost it is taking 418 and straight line distance is 444. So in this approach we are getting with the straight line distance 431 only, but if you take the normal path cost it is 450. Path cost here mean if we sum up 40, whatever the distance from A to E node, E to E to F node and F to I node, it is nothing but the path cost. But here it is mentioned differently. Path cost here mean straight line distance. Straight line distance if we consider. So from E it is 253 and from F it is 178. If we add up that, we got 431. So in this case the straight line distance is 431 and if we take the normal path cost it is 450. But when we take in this approach the straight line distance is 444 and path cost is nothing but 418. So this we got higher one, but this as per the normal path cost it is 418. So that we can't say it is an optimal one. Why? Because here it looks to be optimal, but when we take a different path, so it may not be an optimal one. The normal path cost is even lesser than the straight line distance. Here in this path we got the straight line distance a good one than the normal path, but here we got that the normal path cost is even very much lesser than the straight line distance, so that we can't say this is an optimal one. Next, is it complete? The second one which we need to check is it complete? Suppose that we have just modified here. C is 329 earlier, straight line distance, but we have modified it to 250. We made a change here, 250. And even whatever the tree which was mentioned earlier, that remained same. That remained same. And if we just continue the process of searching for the solution. So as we know, first among these there is nothing but the three paths, that is C, E. So if you take this tree, there is a path to C, E and B. So here the straight line distance of C is 250, E is 253 and B is 374. Among these three, C is lesser, so that it will choose the path C. It will choose the path C. And from C it can go to either D or it can even go back to A. So from C it can take path to D and A. So if you take A, it will not take A. Why? Because always A will be having higher straight line distance. So it will not go to A, and the other path is nothing but D. So 244, which is lesser than this one, so that it will take the path D. And next from D actually there is no path mentioned. It can go back to C only. It can go back to C only. So what it can do is it can go back to C. From C, what are the two paths which are available? From C, it is path to D and path to A only. So A, it should not go at all. So it should go to D only. So that once again it will be going to D. So like that it will be repeating C, D, C, D, C, D. So which becomes an infinite branch. So in this case, what we can say is it is not complete also. That means sometimes we may not get solution by using this greedy first search, greedy best first search. Next, conclusion. In conclusion, we can say that greedy search is not optimal. And next, greedy search is incomplete. Why we are saying incomplete means sometimes it may not give the solution and it will be going on repeatedly infinite state itself. And next, without systematic checking of the repeated state. If we have repeated states, it is nothing but incomplete. Next, optimal, as we have seen one example, we will be getting a best solution sometimes using the best first search, but sometimes the normal path cast approach will give you the best solution, so that even it is also not optimal. So the complexity here is nothing but O of b power m, where b is nothing but the branching factor, m is nothing but the maximum path length, how much distance it need to travel in that path to find the solution. So based on that we'll get the time complexity as well as the space complexity. So this is about all about the greedy best first search. In the next video we'll see about the A star search, as well as one more informed search strategy is there, iterative deepening A star. So that also we'll discuss in the next video.